Hello, everyone, and welcome. It is a very special day for us here at the Knowledge Bolide. We have a very esteemed guest with us today, and we're going to have a conversations with classifiers. And this is a gentleman I've actually wanted to get to know, and actually, I'm surprised we haven't run into each other more in the last couple of years. But we are joined by Dr. Chris Hurd of University of Alberta. We're gonna introduce him a little bit. Sue's gonna tell us a little bit about why I'm so geeked to have Chris here today. And he's asked us to call him Chris, even though in the next couple of slides you're going to see why I feel intimidated calling him Chris. But Sue, could you please tell us a little bit about our guest?
Yes. Okay. I'm just going to share a few fun facts about this. A very accomplished individual before we get started. So Dr. Hurd is originally from Ottawa, Ontario. He studied geological sciences at Queen's University, and then he studied earth and planetary sciences at the University of New Mexico. Dr. Hurd is a former postdoctoral researcher at the Lunar and Planetary Institute. He is currently professor, faculty of science at the University of Alberta. He was a Smithsonian Institution Senior Research Fellow. Now, I just checked the MEPL the other day, and he had 381 mentions in the MEPL, but knowing how busy he is, there could be more by now. So I'm sure there are more coming. He is an internationally recognized expert in the geology of Mars from the studies of Martian meteorites, and which is kind of be our main topic of conversation tonight. Dr. Hurd was a member of the NASA Mars 2020 Perseverance rover mission as a participating scientist and expert in return sample science. He was a recipient of the 2013 Faculty of Science Research Award. He's an elected fellow of the Meteoritical Society since 2016, the principal director of the Institute for Space Science Exploration and Technology. Okay, I could go on and on. There's more, but we're gonna just we're gonna focus on. What was that?
I was gonna say we're gonna call him Chris tonight.
Yeah. So yes, exactly. This is why Topher and I are a little intimidated. Very accomplished and a very amazing individual. So I'm gonna just turn it back to Topher so he can quickly give himself and our company, our channel, an introduction, and then we'll get started.
Well, we are collectively the Knowledge Bolide crew. We started hanging out every single Wednesday and haven't missed a week we're at 4.5 years now. So we talk science every week, we talk meteorites every week, and I'm kind of the leader of the pack here. So I look at myself as a community builder and an educator. I have 17 mentions in the Met Bowl, and I'm really proud of the media I've created around meteorites and meteorite education specifically. So there's about 450 videos on our channel. We have over 18,000 subscribers. I really want to break 20,000 in this year. So anyone watching this, please subscribe right now. 2.5 million views, a bunch of hours. But the cool thing is we're watched all over the planet. There's constantly viewers reaching out to us from different countries, and I absolutely appreciate and love that. So that's enough about me and us. Now we're trying to get to know you on a little bit more of a personal basis. So I haven't had a chance to work with you myself, but these are some of the doctors that I've worked with already, and these are people you probably know very, very well. These, I wouldn't say they were mentors of mine, but inspirators of mine. Can I ask, when you're starting out in your career, or even now, who do you look up to? Who served as a mentor to you?
Yeah, well, I mean, I have to say that, well, growing up, it was my dad. My dad is a retired curator of the National Meteorite Collection of Canada. So that's why I grew up in Ottawa. That was his job. So I grew up around meteorites. And he's retired now, but I see him all the time. And then when I was in, I didn't really know whether, I knew I wanted to do something to do with Mars. I didn't know I wanted what exactly. But I did know, like at the age of 13, I wanted to do something with Mars. I thought that would be really cool to study the geology of another planet. And Mars, just has this attraction, as many know. And so I thought, when I go off to university, I want to be able to do geology. That was kind of a given. But then I wasn't sure about getting into meteorite research. And so, but ultimately I ended up at New Mexico for my PhD, and with Jim Papike. He was the former director of the Institute of Meteoritics, and he was an incredible mentor to me. He was phenomenal. He was really busy too. Maybe I take after him now. I don't know. Like looking back, you kind of think, well, maybe that actually, because he was on like 7 NASA committees or something at the time when I was his grad student. But he gave me a lot of leeway to do the stuff that I wanted to do and to kind of make mistakes as well. And was just a really, really good mentor. So I also try to emulate him seriously speaking, like I do try to emulate him as a mentor to my own students as well now.
That's fascinating. That's great. Yeah, pass along to the next generation. Because that's one thing we're not going to talk about now, but one of my fears is there's not enough new and young meteorite classifiers coming up. But we'll get into that later. Personal question: do you collect meteorites at all?
You know what? I actually don't. I don't. I guess it's funny because I thought, well, yeah, I guess because I kind of grew up with them. Rocks and minerals for sure. I love geology of all different types, and I think I find rocks and minerals just fascinating. And I think what is so interesting is that because you can tell so much from rocks and minerals wherever they're from on the earth about the processes, you can do the same with minerals and meteorites. But I've never actually gotten into collecting meteorites. And I guess in part because I've been here at Alberta for 21 years, and I've been in charge of the meteorite collection here and growing the collection and classifying things. This was pointed out. I didn't know it was 281 mentions, by the way. That was news to me. I just kind of do the classifications and then like don't think about it. But all that kind of thing. I'm around them all the time, so I don't really have a personal collection for that reason.
You'd be a hard man to impress with a collection at your house. When we first started arranging this conversation, you asked me, we reached out with a misunderstanding about you, which is a very, very common misunderstanding about Chris. Everyone who has an iron meteorite that wants to get classified, you got to go to Dr. Hurd in Alberta. Dr. Hurd in Alberta, iron guy, iron metal, metallurgy. That's not who you are. That is you, but that's not really what your desire. And you talked about Mars. Why are you known as the Iron Man?
Well, yeah, that's a great question. I didn't realize I was known as the Iron Man. That's kind of cool. But yeah, it's really because actually it started with Whitecourt. So Whitecourt was a discovery that some of you may know about that is an 3AB iron, but it formed an impact crater northwest of here in Edmonton in Alberta. It's a really cool little but impressive, 100 foot across meteorite impact crater that where, because in contrast to meteor crater there in Arizona, where there's nothing left in the bottom, there's shrapnel pieces around, and so I guess actually kind of like meteor crater in Arizona, there's other meteorites associated with it. But most of the meteorites are like shrapnel pieces from the explosion. Anyway, we discovered that, or I helped to describe that crater in 2007, and then to classify the meteorite through actually originally INAA, which is the method that John Wasson used at UCLA for a long time. So we did some of those early, and then we moved on. And so what happened was I recognized that there's a need, especially after John Wasson's passing, but even before that, there was a need for additional people working on classifying iron meteorites. So we developed a dissolution method where we take a small chip that's like 250, 200 milligrams sort of thing, a small little sort of millimeter sized chip, and we dissolve it in acid. And then my colleague here runs it in the lab, runs the concentration, determines the concentrations that way. So it's ICP-MS is the name of the method that we use. And so we've further developed it, kind of refined it, and over the last several years.
And is that no one else is doing that though? I mean,
there are others that are doing it. I mean, yeah, there's other people who are doing it. I guess I've been able to kind of build up more of well, obviously, reputation.
Seriously,
More,
I really,
more, yeah.
I
But
really thought
we
you were
do them
into
in
irons
batches as
only.
well. So yeah, we do them kind of in batches, sort of like they do at UCLA and batches for neutron activation analysis, but we sort of do them in batches because it makes it worthwhile to sort of dissolve a bunch of them all together with a standard, and then run them sequentially, so sort of 15 and 20 at a time. So we've kind of developed that capacity now, and with the interest, it makes it possible to do that. I guess I'm just saying that it's become an interest of mine. It's part of the classification that I do here, and also because classification helps to grow the collection here,
Yeah.
I've actually been able to pretty much triple the size of the collection in terms of number of meteorites represented at the University of Alberta since I've started.
Well, that's a nice win-win, but let's get on to the fun stuff. This is, I would like for you to take the next couple minutes, just whatever you'd like to talk about, but your passion is the geology of Mars. And this is something that blows my mind, actually tracking meteorites back to their source craters.
Yeah, this is okay. So this is to give you a sense of how significant this is for me personally. I mentioned already how interested I was in working on geology of Mars, and then doing a PhD on Martian meteorites at New Mexico. Graduated 2001. At that time, there were like 13 known Martian meteorites, and only the kind of the first couple had come out of Northwest Africa. So like Dar el-Ghani 476, SAU 005, where and then the Los Angeles meteorite, it was also recovered around that time. So there's like the really historical falls, and then the Antarctic ones, and then these hot desert ones were starting to be discovered. So there was a lot. I knew it was really great, and then like I loved studying them because they're the only samples we have from Mars till we bring samples back, right? So but since that time, and even with all the other things that I've done, the other things that I've already mentioned, other research that I've done on other opportunities like the Tagish Lake carbonaceous chondrite, all the other stuff that we've done with growing the collection, et cetera, the various student projects, the constant thread for me has been rocks from Mars. And even my involvement, as Sue mentioned, on the Perseverance rover mission continues to be, what are we going to do? How do we collect the best possible samples to bring back to Earth? We can come back to that later. But in the meantime, it's like, you know what? Now we have like 200 Martian meteorites. And over these past several years, in about 7 years ago, I took a 6-month sabbatical to think about this problem, to go, okay, how can we actually start to link where a specific meteorite might come from on the surface of Mars.
Yeah.
Partly because I've been studying them, and then you start to work out, you try to get as much information as possible from these things, right? From a single little thin section, you're just analyzing the crap out of it, every aspect, trying to figure out, okay, how did it form? What happened to it afterwards? Maybe where did it sit near the surface? What kind of things? And then then we know that these things got blasted off the surface by an impact. So we have this like sequential history, and it's like, well, can we the original thought was, can we map that sort of history back to the most likely spot on Mars? And then I got into thinking about it more and realizing that the information that we have contained in the meteorites can kind of be decoded, and we can link the information, different aspects of different parameters of information in the meteorites to these events. And the missing link in all of it was in right around that time or just after that time, this was like 2018, 2019, there was more research being done by Jay Malosh and students at Purdue University on modeling that impact process that blasts these rocks off of Mars, and getting a better idea of what happens when those rocks get blasted off Mars. So yes, in this image here, and this was a painting that a student did, a former student of mine did last summer when we were developing all these ideas. In the upper right there, you see the impact process. And so the idea is that something that rocks near in kind of a ring near the surface have specific conditions that don't basically vaporize them. They get preserved, and they get kicked off the surface of Mars. They get accelerated fast enough to leave Mars gravity, which is crazy to think about in the first place, right?
Yeah.
But we've refined the modeling of that to say that okay, so that particle, and in this case, we sort of highlighted a boulder that got blasted off, and then in the inset, it becomes a meteorite that falls to Earth in prehistory, falls on the Antarctic ice cap in this case, and becomes elephant moraine 7901, which is the famous one of the first sort of famous ones to be recognized as being from
A
Mars in the
really
first
cool
place.
picture.
Yeah, and so, but like, what happens in that shock process? What happens in that impact crater when it gets blasted off the surface? We have a better idea of it, and by interrogating the shock veins, which many of you are familiar with, these shock veins are pockets that you see in a lot of Martian meteorites, especially Shergottites. They have information obtained like inside of them that we can decode to say, okay, this is the sort of the pressure wave, like the peak pressure that the rock experienced during this shock event, and the temperature, and how long that shock wave how long it took that shock wave to pass through the rock. And it's like 10 milliseconds, like it's really, really short.
Jeez.
But we can actually tell that from the minerals, from the stuff inside of those shock veins. So that's like, I call that the missing link, because what the modeling can do is to say, for a given meteorite, let's say it's elephant moraine 7901, it has such and such peak pressure and amount of time called dwell time, the amount of time the pressure wave took to pass through it, and we can use the model, and we can like look at all the options for the size of the impactor that could have resulted in those conditions. And the size of the impactor is directly going to determine the size of the crater, right? So now we can say, no, we can't say like the crater has to be like between 8 and 8.5 kilometers in diameter. No, it's bigger than that. It's a bigger range than that. But we have a range of impact crater sizes then for, say, elephant moraine. Now, the other part of it is the basics of Martian meteorites, which is that we know that they're igneous rocks, the vast majority of them. The only exception is Black Beauty and Pears. And then the vast majority are really young. Like there's a whole bunch that are a few hundred million years, most of the Shergottites. There's the Knocklights and Shastignites at about 1.3 billion. And then the augite-rich Shergottites, which are 2.4 billion. And then Allen Hills 84001, which is the real oddball, that's 4.1. But the vast, like 98% of all Martian meteorites by number are much, much younger.
Yeah.
And what we call the Amazonian age, less than 3.5 billion years old, essentially, which is the sort of division, the epoch that we talk about on Mars as being the youngest era or epoch is the last 3.5 billion years, the most recent 3.5 billion years of Mars history. Whereas only a quarter of the surface of Mars is that age. So we know this. We know Paul Warren talked about this like in the 90s, that there's a bias in the samples that get delivered to us, because this thing that you see right here is a really violent process. So only the strongest kind of rocks are going to survive. So it follows that we selectively get nice, young, fresh igneous rocks from Mars. So now that we have like 200, we can say that even more definitively. But now we have more information too. We have the ages, the crystallization ages. And then we also have, and this is another key part of the puzzle, is the cosmic ray exposure ages, which is essentially how old is that rock? How long did it take that rock? How long has it been since that rock got ejected from Mars, like we see in this painting? So we can group all 200, most of them all actually, of the 200 Martian meteorites can be grouped into about 10 different bins in terms of how long it took them to get from Mars to Earth. And that we translate into 10 different impact craters. So for 200 Martian meteorites, we're looking for 10 impact craters.
Wow.
Right? So now all of a sudden that we're narrowed it down. Now the other thing is to look at what impact craters they could be. And so fortunately, a colleague of mine, Livio Tornabene, was now at Western University in Ontario. He has been making the database of impact craters for the last 10, 15 years that are the freshest craters on Mars. So because we know from the cosmic ray exposure ages that the oldest is like 18 million, like 20 million years is the oldest in terms of amount, like when it was ejected from Mars of all the Martian meteorites. Most of them are a million, 2, 3, 5 million. The knocklights are 11 million. Elephant moraine is like 750,000 years. It's really quite recent.
Yeah.
And so then you can start to say, okay, that means that we're looking for like the freshest craters. And because we know that these are Amazonian igneous rocks, they have to come from Tharsis and Elysium. They have to come from surfaces on Mars that are younger igneous surfaces. And so when you take all those fresh craters and you say the freshest of the fresh craters sitting on Tharsis and Elysium, you have 15 craters to work with. So you have 15 craters and you're looking for 10 total craters, but really for the Shergottites, it's like 8 craters. Okay. So you have 8 craters out of 15 that you're trying to then narrow down for the Martian meteorites. And so then it actually becomes a problem that you can address.
Wow. Yeah.
So then we use some other parameters,
Jeez.
but then we basically come up with the 5 that you see here. The 5 plus Karatha. Karatha at the bottom there is the one for Black Beauty that was published previously, but the top ones there, Chakpar, Tooting, Domini, Kotka, Corinto, these are the ones that we identified as being the sources of 5 of the 8 Shergottite groups of Shergottite meteorites ejected from the surface of Mars.
Wow, you have just blown our minds. It's amazing because I actually spent the weekend with a bunch of smart scientists with the B612 Foundation, excuse me, and the Asteroid Institute. And it's amazing the questions that can be asked based on something that's learned. Something as small as a shock vein can get you all the way started in this path that brings you down to these 5 ejecta points for our Shergottites.
Yeah,
that's crazy. Wow.
I know, and I love it. I love it because it's all like it's where where we started from. It's still where I started from in this whole question. Like, what is the history that is recorded in the meteorite that you can use to kind of unravel and link it back to specific events, right, and locations. So that's, and then, but a lot of it has to do with, more the fact that we now have, especially in the last few years, have more remote sensing, better data from orbit of these craters on Mars. Livio is really good at even asking, had been asking Mars Odyssey to target specific areas so he could get better images on these fresh craters, things like that. And then, of course, more meteorites being recovered and more data on the meteorites themselves. So yeah, it's become a possibility. And those other 3 craters that we haven't identified yet, if you actually look in the supplemental information from the paper, we have some possibilities. So the excitement that I have is that we're getting that much closer. And it's also a framework, right? Like anytime that we find a Martian meteorite of any type, the things that we need to be looking at obviously are like classifying it, what are the minerals, how does it fit in, but also we should really prioritize that crystallization age, that cosmic ray exposure age, to figure out kind of what group, because the cosmic ray exposure age, we group it together with other meteorites immediately from the same impact crater. And then the really cool thing is that the impact modeling, so then the third thing that you need is the shock effects. You need to and I know they're not always in every meteorite, but if you can find shock veins, especially nice thin shock veins, those are the best. Those preserve the best information. But the thin shock veins that you can then interrogate to say these are the conditions under which it was ejected. But the really cool thing, the impact cratering model is actually really sensitive to the depth of the rock before it actually was ejected from Mars. So you see elephant moraine sitting there. If we have other meteorites from the same event, we could maybe figure out where they were relative to elephant moraine while it was sitting on the surface before it got ejected. Wow. So we could even do like pre-impact stratigraphy to say, okay, and this has started to work out for Tooting crater, because Tooting is the source of a lot of these so-called depleted Shergottites like T-cent. There's a whole suite of them that were all ejected around 1 million years ago. And so in that case, it seems like T-cent at about 600 million years old was deeper down than some of the other NWA meteorites that are probably from the same event. And so our study kind of corroborates other studies that shows that, yeah, these things were probably in like lava flow layers relative to each other before everything got blasted off the surface. But we can actually do more of that if we have more information from the meteorites. So it kind of provides a direction that we can take the research to test this, to see whether, all of these meteorites of a particular character or type are from the exact same spot on Mars.
This is truly fascinating. I could, at the sake of my crew, I could go on and on with you, but we actually have some prepared questions from members of the crew. We got Jules coming first. Jules is very humble, so I'll give her an introduction. She is a world-class cutter and polisher of meteorites. She has 2 mentions in the Met Bowl. We call her Mrs. Buttersworth because she gets them so smooth. She's the owner of Space Jules Meteorites. So, Jules, are you with us?
I am. Hello, how are you?
Hey there.
Hello, Dr. Hurd. My question is, was there anything specific that led you to the interest of studying Mars and Martian meteorites? You kind of went over it a little bit, but I mean, just the tipping point, like what grabbed you?
Yeah. Yeah. I mean, I had mentioned, growing up around rocks and being interested in geology and knowing what a meteorite was, et cetera. But I also was reading science fiction. I was reading Isaac Asimov and other stories, and around, it was really around the age of 13 that I think I mentioned that I decided, this is what I want to do. I want to study Mars. I didn't know anything about Martian meteorites. In fact, it was kind of around that time that scientists were even figuring out that we even had these things. But yeah, so I decided, this is what I'd like to do, is study Mars, because Mars is Earth-like in a lot of ways, but in other ways it's not. It's so inhospitable to life today, and it's one of those huge questions of comparative planetary geology. Why did the Earth go one way and Mars, and for that matter, other planets, go a different way when they started with similar material at the same time, that sort of thing. So, and then when I wanted to do grad school, I was the question was put to me: do you want to work on a mission, like mission information, remote sensing data, that sort of thing, or do you want to work on samples? I'm like, I want to work on samples because the samples are where it's at. And of course that's worked out. But yeah, so that's the reason why I decided to go to New Mexico and work with Jim Papike, who was looking for a student to work on a particular aspect of meteorites from Mars.
Awesome. And I think Jules has another question as well.
I do. What challenges do you face in classifying potential Martian meteorites, such as bureaucracy, lack of funding, limitations in technology? And Topher added this one because he's funny, not being on the planet Mars, et cetera, because he would rather live there, I'm sure.
Well, I mean, there's obviously there's obviously being able to get the samples. Funding hasn't been too bad. I've been fortunate to get research funding. One of the reasons why I also do classification, because it opens up possibilities for additional research, especially if it's a newly classified Martian meteorite. In terms of technology, we have a lot of what I need here at the University of Alberta, and then I lean on other colleagues to do other things. So yeah, I mean, there are some challenges, but generally things are good in the Martian meteorite classification world.
His life's so good when he takes a 6-week sabbatical, he just works on the biggest thing ever.
Well, okay, it was a 6-month sabbatical, Topher, but it took 7 years to get the project done. So.
Thank you, Jules, very much. Next, we have Dave. Dave is excuse me, he's a museum guide at the Griffith Observatory, and he absolutely loves doing education and outreach. So, Dave, are you on with us?
Yes, I am. This has been a burning question for me for a while. any of the rovers found material that matches any of the SNC meteorites that have been found on Earth?
Yeah. Yeah, that's a great question. There's one that I'm aware of. It's called Bounce Rock, and it was found by the Opportunity rover, the Mars Exploration Rover. Opportunity rover. It was called Bounce Rock because that was a rover that landed by airbags in 2003, and they figured that the airbags actually bounced on the rock before, like the rover inside the airbags bounced on the rock before it came to rest. So when they went and explored it and analyzed it, it has the closest composition overall to what we see in the Martian meteorites. And in fact, there were comparisons made in a paper to Elephant Marine 7901. However, nothing since then, really. All of the igneous rocks that rovers like the rover I'm involved in here, Perseverance or Curiosity, the other igneous rocks that's the Spirit rover, Opportunity's twin, analyzed, they are all very different. And so that's actually a really interesting question, and in fact a driver for how we choose the samples that we're going to take with our rover Perseverance. We basically have said through, and it's not just me, it's like the community sort of coming up with what are the sort of characteristics that we want in samples we return from Mars. Obviously, we actually want to expand to sedimentary rocks, the ones that are more likely to have evidence of ancient life. But if we're going to collect igneous rocks, we want to make sure they're different from Martian meteorites. Because that bias that I mentioned does really seem to bias towards the young igneous rocks from these other specific areas on Mars. And that's a key thing to find and understand, because if we, and with Perseverance, the first samples we collected on the floor of Jezero crater turn out to be igneous rocks, probably much older, with some similarities to Martian meteorites, but some obvious differences. So if and when, hopefully when we get those samples back to Earth, we'll be able to do a one-to-one comparison and really try to understand why it is that those igneous rocks in different parts of Mars have different characteristics to the igneous rocks that are preferentially sampled and delivered to us as the meteorites.
Very interesting.
Thank you.
Thank you so much. Pat is our next questioner. Pat actually has a co-classification, easier for me to say, to his name. He's the owner of Meteorites Lab, and he has 6 mentions in the Met Bowl, and he loves going to the Meteorological Society meetings. So, Pat, are you with us, sir?
Yes, I am.
Welcome.
So, Chris, I think you touched on many of the points of this already, but my question was, is our view of Mars warped because we have so many of these SNCC meteorites that are really so similar, and I guess maybe are excavated deeper?
Yeah, well, they're excavated more shallowly, actually, but they're from a different part of Mars, and that's the warped view that we get. That's the bias that we get. So in essence, yes, it is. And it has been pointed out by other people. Hat McSween pointed this out years ago in a paper when he sort of synthesized some of the information from the rover missions on the different igneous rocks. And the conclusion is that the Martian meteorites are not representative of most of the igneous rocks at the surface. So there's something different going on there. And again, that to me, that's just really intriguing. That to me is, we have to think about what it is, what differences are there? Like, what is it that's making the Martian meteorites have these different overall characteristics relative to the igneous rocks that we have so far only analyzed at the surface and not brought back yet.
Right. Okay. Very good. Thank you.
Sometimes the conversation leads right around to the point where we actually answer the question before we ask it. So thank you, Pat. I appreciate it, buddy. Mike is he is our instructor on the Knowledge Bolide. He is our crew geologist. He has a Bachelor of Science in Geology. He's a little accomplished meteorite hunter. He went off a few years ago and found a bunch of them. So he's also authored some meteorite content online magazines, and he has 4 mentions in the Met Bowl, and he's a hell of a guy. So Mike, welcome, buddy.
Hey, thanks, Chris. Great seeing you. So I had a question, and it kind of touches on some of the things you mentioned. You mentioned the different suites of Martian meteorites we have, and how it's expanded. How we got 8159 all-giant basalt, and how we have Allen Hills 84001 ultrapyroxenite. So you mentioned on Mars, the samples that they're targeting are different samples. So that's all going to take time to get back and study. So my question to you was, if you could find any type of rock in the form of a Martian meteorite right now, that would be exciting to you. What type of rock would that be? Would it be a granite? I mean, I know obviously lacking plate tectonics, Mars doesn't really have or isn't thought to have true granites. What type of specimen would really open the door for new science in the form of a found meteorite?
Yeah, that's a great question. Yeah, I mean, probably something really old, and of a different igneous rock type. There are sort of intriguing rocks that have been observed by rovers that, including Perseverance, relatively recently. There's like a salt and pepper rock that we saw,
Yeah.
boulder that we saw. That's we did actually, unfortunately, didn't have a chance to go stop and look at it, but just as a sort of an aside, we are hoping and anticipating that because we're heading up the stream bed onto the crater rim, and we've come from downstream, that rock will be represented in outcrops further up, and if we see it, we'll definitely stop. But that type of thing would be really interesting to find, because we're always looking, again, because we have this bias in the Martian meteorite suite, we're looking for the rocks that are different. So older, maybe ideally even like early crust of Mars sort of rocks, something that can give us new insights into what was there in the early stages of Mars. And all these igneous rocks come as magmas from the interior. And so, one of the ideas is that the Martian meteorites come from a certain type of are part of the mantle of Mars, and other ones come from other parts of the mantle that have had different histories. So anything like that would be intriguing. So again, I guess it just reiterates that one of the things that we need to do after classification is really figure out how old the rock is and what interesting characteristics it might have. I'll also say that I'm not shutting the door on sedimentary igneous rock, sedimentary meteorites from Mars. Okay, I'm just saying that it's not as likely. And the regolith breccias is kind of an example of that. It's so interesting because it's so different from the other Martian meteorites that we have. So we should be prepared to see if to see something else, other breccias, or like a sedimentary rock that's nicely. It would have to be really nicely sort of cemented to be strong enough, most likely, to make that trip. But that obviously would be a huge class expanding new find, absolutely. And would allow us to get your last point, it would allow us to obviously ask these other questions that we're trying to ask when we're trying to anticipate when we're collecting the samples with the Mars rover with Perseverance. Like what are the conditions of water? What was there evidence of ancient life? What was the habitability of the rock, etc.
Thank you very much. Thank you, Mike. Bruce was going to be here tonight to ask a question. Unfortunately, he wasn't able to join at the last minute, but he has a strong interest in astronomy. And his question was, because you mentioned the crystallization age. Can you explain what it is and how you guys measure it?
Yeah, for sure.
Excuse me, you also mentioned there was another age, the age basically of flight.
That's
That's
right.
a different age, correct?
Yeah, that's right. Yeah, they're two different ones. So like Zagami is 165 million years old, and that's been determined from, in terms of crystallization age, that's been determined actually from a number of different systems. So what we do, probably most familiar is uranium lead. Uranium decays to lead at a certain rate. It's been used many times for rocks on the Earth. There's other systems as well where a radioactive isotope of rubidium decays to strontium. Another one, samarium, decays to neodymium. These can all be analyzed, that the amount of parent left, like the amount of uranium left, and the amount of lead that is a result of the decay of the uranium, those can be measured in the rock in different minerals typically, and then you can use that to get an age. You can figure out when those minerals were had all formed together. So that's our crystallization age. Now, one of the other things I've worked on is using uranium lead in a mineral called bedellite. It's sort of like a version of zircon that you find preferentially in Martian meteorites. And it's really good at recording, just on its own, it's good at recording uranium lead ages. So, but all of that's to say is those are a number of ways you can approach it, where you can get at the age at when those minerals crystallize together. Now, the ejection age is essentially the result of exposure to radiation in space, galactic cosmic rays, that sort of thing, of that rock as it travels from Mars to Earth. Basically, and it's not like it sort of gets ejected off of Mars and like plots a course.
Yeah.
It heads for Earth, right? It gets ejected from Mars, and then probably gets ejected in all directions, and then the certain proportion of them end up in these orbits that'll go around the sun, and then eventually that orbit will cross the orbit of the Earth and fall to ground as a meteorite. But in that time that it's sitting there in that orbit, it's accumulating radiation from these galactic cosmic rays, and then when it falls to Earth, you can measure that and determine the amount of and use it as a clock. There's certain isotopes that you can use as a clock to determine how long it was sitting in space.
This is fascinating. I really appreciate it. Cal is another member of our crew. He is a graduate of MIT, member of the Meteoritical Society, International Planetary Society, and a bunch of other stuff. He's very active in education outreach, and hopefully he's here. Cal?
I am.
Awesome.
And so I think you've answered this question in a number of ways, but for a simple outreach type answer, what is the range of ages of the Martian meteorite subtypes? Are they all the same, or are some markedly different?
Yeah. So the Knocklights and Shastignites all have the same age, crystallization age of 1.3 billion years, and they all actually have the same ejection age of 11.5 million years. So that's one of the reasons why you can group them together and say, yeah, these are definitely from the same spot on Mars. And other people had looked at those rocks before and gone, they're so similar to each other, they can be related through igneous processes. So they're probably from the same sort of magmatic system. But that's kind of more, I'd say that's kind of more the exception than the rule. The Shergottites tend to group differently. There's several Shergottite groups in terms of ejection ages, from the Elephant Moraine 701 that I mentioned, that's 750,000 years, and there's a bunch of 1 million, and then there's another group that's 2.5 to 3.5 million years old, right around 3 million. That includes Zagami and Los Angeles, for example. And then there's another group at 5 million. So there's a range of ejection ages, and then within that there's a big range of crystallization ages. So it's not like systematic cut and dry necessarily for most of the Shergottites.
Okay, so it's complicated.
Yeah, it is complicated, but it's interesting when you think about it, right? Because the fact that you have like T-Cent is part of this group that got ejected. I mentioned before how it could actually sit in the stratigraphy. And our results are consistent with that. Like, it was probably buried about 25, 30 meters depth. It has an age of about 600 million years, but the age of the rock that was probably the top, I think it's NWA 1183, it's about 350 million years, I think, give or take. So, and the other ones probably sit in between. So and those were all ejected together, but it's cool because it kind of, you can paint this picture of, okay, and those are from Olympus Mons. Like those you can actually think, okay, Olympus Mons was probably, having these lava flows coming out over time, and maybe nice thin lava flows that are coming out over this. And then the Tooting crater happened and blasted these things off the surface. So you actually do kind of get this picture in your mind, start drawing cartoons about what was where.
Wow.
Thank you.
Fantastic, man. Well,
We'll keep
we're
them up.
definitely going to limit Cliff's questions. He's a very deep person and had 4 of them, and it would take you an hour and a half to answer his questions to his satisfaction. So we're not going to do that. But Cliff does have a question. Is this one that you want to ask now, sir?
Sure. So the NWA 7034, if I understood correctly, it contains a lot of material with varied ages from 4.4 up to 1.5 billion. What processes on Mars would have formed a composite material like that without ruining the records of the ages that in the geologic processes that it took to assemble them? Maybe I'm biased thinking about Earth, but I'm a little surprised material that old came together in a composite like that, and we can still decode it that way. So I was curious,
Yeah.
what happened on the Martian surface or subterranean areas that formed that?
Yeah, I think that's a great point. And I think the detailed studies of that rock suggest that it was probably impact mixing originally. So impact ejecta, fragmentation from impacts, which of course are more numerous in the older terrains. And then when it was assembled, there was a certain amount of heating, sort of like almost like a hot ash deposit, where you form a tuff, a welded tuff, that sort of thing. Not quite that hot, but warm enough to cause some of the really fine material that's between the clast to recrystallize and make it sort of indurated. But you're right, it's a very interesting rock for that reason. And there's also this idea and there has been this idea, this paradigm that Mars was covered with water early in its history. And because we see some of the older parts of Mars have evidence of clay minerals and things like that from orbit, as indicated from orbiting spacecraft. But here's a rock that has clasts in it that, as you point out, have 4.4 billion-year-old zircons in them, and presumably by inference, the other sort of bits and pieces in there. And yeah, there's a little bit of water in there and more than typical Martian meteorites, but it's not like it's completely full of clay. So it's actually a very intriguing rock just for that reason.
Thank you.
Awesome. I think we have some questions coming up about water too. Dr. Chris would like to ask a question. I thought it was interesting. He has 7 published books on cybersecurity, so I didn't know that until this morning. Chris?
Hey, thanks. And from one Dr. Chris to another, I appreciate you being here with us tonight. So, I'm going to start with a very non-controversial statement. Mars and the Earth are different distances from the sun, from each other. So the question I had was really, can Martian meteorites have features that show how Mars formed differently from Earth as a result of that distance from the sun? Are there unique properties there? And if so, what might some of those be?
Yeah, it's a good question. I mean, there are some that could be the result of the distance from the sun. The oxygen isotopic composition, offset from the composition of the Earth and the Moon, is one that might be. Other stuff's really subtle. And also it's sort of obscured by the fact that we have to sort of see through the meteorites, sort of peer into the meteorites and try to infer what their composition, the composition of the original magma was, and what the composition of the mantle was that they came from. But there's things like the relative proportion of certain elements, so potassium, sodium, that sort of thing, more volatile, so-called more volatile elements that seem to be different from the Earth. So that's what I mean, it's subtle. Like when you look at these things as igneous rocks, they are very similar to certain types of igneous rocks we have on the Earth. But when you start to delve into them in more detail, that's where some of the subtle differences come in.
Thank you very much.
Sir.
Thank you, Dr. Chris and Dr. Chris. Ken is retired and loving it, but he's a very enthusiastic meteorite collector. Ken?
Hey, how you doing, guys and girls? Dr. Hurd, appreciate you being on this program. You are just blowing my mind, man. But what I'm wondering, real simple, what happened to the Mars global ocean or oceans?
Yeah, the global ocean, the Northern Ocean, is a concept that was developed after some of the early studies that showed that there's these big channels that were carved at the edge of the southern highlands there, kind of along what's sort of shown as the shoreline of this Northern Ocean. But I haven't studied it myself, but my understanding is that that ocean could have existed if all of those channels were operating at the same time. Now, the thing about the channels is that they are what are called catastrophic outflow channels, and they're probably not from accumulation of rainfall in the southern highlands flowing northward into the northern lowlands and filling the basin. They're probably from things like magma coming up from underneath, or impacts obviously from above, that cause sudden flash melting of ice that's buried in the crust that would then flow out across the surface and then head downhill, which would be into the northern lowlands. So that's what I mean. And so it's unlikely that all of those would be operating at the same time. So people have looked for putative, have looked for shorelines, sort of features that would indicate that, you actually had an edge to this Northern Ocean. And some people claim they found one. Other people say, no, it's not conclusive. So I don't think there's anything really conclusive that said that there was a Northern Ocean on Mars. It's an interesting idea, though, and it's definitely inspired different types of science fiction stories about the planet too, about sailing the Northern Ocean. But there's nothing, as far as I know, that's sort of conclusive on that.
Thank you. Thank you.
I don't know if Scott is here, so I will probably ask his question, but
Scott is here, actually.
Oh, awesome. Yeah. I'm very glad to have a guy that has an asteroid named after him here. So take it, Scott.
Hey, thanks. Hey, this is really great, Chris. Appreciate your information. We've talked about water a little bit on Mars, and I guess it's disappointing that all of the meteorites are recent magma flows as opposed to older stuff where we could see that. But can we deduce anything at all from the information we get from Mars meteorites, or just Black Beauty, or what can we learn about surface water from what we've got so far?
Yeah, it's a great question. It's there in the Martian meteorites. It's just really subtle. And when you think about it, if you sort of take this idea that they had to be a certain, the rocks had to be a certain competency in order to make the trip, then if you alter them too much, they fall apart and you're not going to be able to record, you're not going to be able to preserve anything that could actually get blasted off the surface. But in the ones that we do have, there are some subtle things. So in the knocklights, for example, you have salts and rust. This is what's called Adingzite, which isn't a mineral, but it's a sort of mixture of stuff that's probably from water percolating through. And then there's some other even more subtle material. In fact, in those shock melt pockets that I mentioned in Elephant Moraine 79001, and T-Cint has it as well. My students, others have shown that there's kind of like a chemical signature almost of maybe some very, very sort of traces of water percolating through in fractures, maybe leaving like imagine, percolating through and decorating those fractures with a little bit of precipitated mineral. But then it gets obliterated during the ejection process, but the chemical signature ends up in the black glass that's inside the meteorite. So it's really sort of subtle and cryptic, but it is there. So it still sort of supports the idea that even recently you have, maybe it's frost, maybe it's not streams, but in recent years, but maybe it's like frost getting into fractures in these igneous rocks as they're sitting at the surface or close to the surface, and making very subtle changes that end up being recorded in the eventual meteorites on the Earth.
Scott, thank you very much, man. Appreciate your question. Cliff, I don't know if we're going to ask this one or not, but let me see here.
Yes, so you had talked earlier, Chris, about how all the meteorites crater candidates are quite young. Unless there was a bombardment epoch of some sort, presumably Mars was getting hit by meteorites prior to that. I was curious why we don't see any meteorites that we think might come from older crater samples as opposed to these new ones. Would such material have just terrestrialized before we ever found it? Like, would the orbits have decayed, or is there some
Yeah.
other reason that meteorites wouldn't show up from older events on Mars?
Yeah, that's a great question. I mean, we haven't found anything like that yet. It is interesting that one of the oldest in terms of ejection age, DOFAR 019, is actually quite heavily altered. It's one of the sort of more altered of the Shergottites, like Earth terrestrial altered. So it could be that's sort of the expiry date for meteorites on the surface of the Earth. So we're not preserving anything older than that. But then again, we do have meteorites on the Earth that have been sitting around for hundreds of thousands of years, up to closer to 1 million years on the Earth's surface. So it's not, yeah. So it's actually, I'm not really sure. And it's another sort of reason why we need to do the cosmic ray exposure of more Martian meteorites to see if we do actually see different ones. But in terms of the collision course aspect and the decay of their orbits, that's a question I might sort of make a note of and go talk to somebody who's an expert in the orbital dynamics of these sorts of things to maybe find out the answer to that one. So you've stumped me on that one, Cliff.
I wasn't trying to stump you, I promise.
No, it's great though. It's actually a really great question.
Thank you.
Yeah. That's why we have to limit him. He submitted 4, like, enough, dude. Next, we have Marissa. Marissa is the secretary of the IMCA, and she's our thin section photography studess. She is amazing at her photography. So Marissa, take it away.
Hello, and thank you for being here, Chris. And my question was, have there been any impactors found in any of the Martian meteorites you have studied? Because we sometimes find like metallic flakes and inclusions in our lunar meteorites. So those are believed to be from the impactors. So I was curious if there would ever be any metals from any impactors.
Yeah, that's a great question. Not that I know of, nothing's been found. For the Shergottites, for most of them, the ones that aren't brecciated, their shock pressures for the most part are really quite high, and so they're definitely from an impact where you have obliterated where you have most likely, I should say, obliterated the impactor. In other words, the energy involved in the impact was such that the impactor was completely obliterated, and you wouldn't expect to see any sort of fragments of it or anything like that. Black Beauty might be one. The breccia might be one where you could look for that. Some people who have studied that meteorite have suggested that some of the glass inside of it are from impact, and that would be sort of prior impacts on Mars that have helped to sort of assemble the bits together, like when I was answering Cliff's earlier question. So, maybe there's hints of it there, but nothing that I found, and nothing that I'm aware of.
Thank you.
Thanks, Marissa. We're going to move right on to Allison. Allison's a meteorite hunter, a jewelry designer, and she also has a YouTube channel and gets more people to her lives than I do. So, Allison, go for it.
Thank you, Chris. I'm really proud right now to be calling you my north neighbor. I've got a little guy up here. We've got a really great science group here in our small town, and there is a student who went to school with my oldest son who is in college this year, and he was nominated most likely to visit Mars out of his graduating class. He would be very interested in the answer to this question. I am personally too. So my question to you is there anything to be learned from Martian meteorites about future life on Mars, about the possible future colonization or terraforming of Mars? Anything that we should, is there a good spot? I mean,
yeah.
Anything that we don't?
Well, that's a really interesting question, and I kind of have to go back to, as awesome as these rocks are, they are a kind of a biased sample suite. So we don't have a full representation of everything. And so that is one of the major reasons why the Perseverance rover is collecting samples. I like to say, you know, with the rover, we get to choose where the samples come from instead of nature choosing for us. But I really think that it's crucial for us to collect the right kind of samples, not just for the scientific questions we want to answer, but also for this future human life, for future astronaut explorers. Because, you know, I used especially the example of the regolith, this Martian soil or loose material. With experience from Apollo, with the Apollo astronauts, you know, that dust got everywhere in their spacesuits. They talk about how it smelled like gunpowder when they came in the lunar capsule, because it's really, really fine stuff and it has particular characteristics. And we know what that is because we've got samples, but we don't have the same kind of thing for Mars. And we don't really have a good idea of what's in that Martian soil and dust. So to my mind, I think it's really important that we get some of that. And that was a driver when we collected our regolith samples about a year and a half ago. We collected 2 samples. We left one on the surface of Mars as a backup, and we have the other one on board the rover. But these are like collected with a special kind of drill bit that allows us to collect loose material. And if you ask me, and I'm not the only one who believes this, but if you ask me, we need to get that back to Earth before we can think about sending humans, because we need to know what's in it, right? We need to know if there's hazards. We need to know, like, if there's the toxicity, all those kinds of things that we have a better idea for the moon.
Yeah, definitely need to have a sample return mission. I agree with you. Thank you, Allison. Appreciate it very much.
Thank you, Chris.
I get to now introduce my beautiful wife. She is co-owner of the company, and she has one mention in the Met Bowl, and she says that I need to buy her a Witness Lunar so she can be a Witness Lunar classification holder. So, Sue, are you with us?
I am. Okay, so I can't take credit for this question. It was asked of one of our first guests, and everybody loved hearing his answer. And so we asked all of our guests this question. What do you think is the most significant unanswered mystery in meteorite science?
In all of meteorite science? Well, probably the biggest one is just how are meteorites from the same group or even different groups related to each other on the original asteroid. So think of asteroid meteorites for the moment. How are they actually related to each other? And the thing that is so interesting now is that we have samples back from Ryugu, Itokawa from the Japanese mission, Hayabusa missions, and we have samples from Bennu, from the OSIRIS-REx mission, and some of those studies are coming out, in fact, and there are similarities to carbonaceous chondrites, CI carbonaceous chondrites in particular, or ungroup C2 carbonaceous chondrites in the case of Bennu, like Tagish Lake or Tarda, some similarities there. So that's really cool. So this like sort of almost like ground truth for meteorites coming from these places where we can actually send a spacecraft to get that context, because in geology that's everything, and that's the driver. You know, that's one of the main drivers for why I started this. Like, couldn't we figure out where the Martian meteorites come from, the actual outcrop or the location or the geologic unit that they come from, because that provides context for the samples themselves. So extending that broadly to different meteorite types is probably the biggest unanswered mystery in my mind.
Awesome, thank you.
I believe I have the honor of the last question. So, given the opportunity, and it would take several years of your life and guaranteed safe return, would you go to Mars and do it in situ?
I don't know. I'm not sure.
Guaranteed safe return.
Guaranteed safe return. I would seriously think about it, but actually, I'd need an additional requirement, which is that the spacecraft would need to be bigger than usual, because I'm 6'5" and and I get claustrophobic, or at least I think about it. When I think about being in like the little capsules, you see the videos of the footage of the Apollo astronauts crammed in there. I don't like that. So yeah, I kind of be.
So we're gonna need a little extra leg room in your
Yes,
quarters.
more leg room. Yes, exactly.
Okay. Hey, I really appreciate. We have some more slides. We're going to ask for more questions and stuff. We're just going to end it here to be very cognizant and respectful of your time. Truly an honor to have you with us today. I really appreciate it. Anyone on the crew, you can open up your mic and say thanks and good night to the doctor. So thank you very much. We hope to have you back anytime you want in the future.
Yes, thank you.
Wonderful.
Thank you.
Thanks, Chris.
Thank you, Chris.
very much.
Thanks, Chris.
Very interesting.
Awesome job, Chris. Appreciate it.
Thank
My
you.
pleasure.
Please
It's always
classify
a pleasure to
sediment-
talk about. Oh, sorry. Go ahead.
Thank you, and I hope you classify a sedimentary rock from Mars soon.
Thanks. Yes. Yeah, the sedimentary rock from Mars or like a witness fall. That's the other thing. We have these fireball cameras that I operate some here and others do it too. It'd be great to have another TSIN type event. But no, I was going to say it's such a pleasure to talk to an audience that is so enthusiastic about the topic. So it's been really a pleasure. So thank you for all your questions as well. Really got me thinking.
We are nerds.
That's great.
Yeah, love it. My
Thanks,
people.
Chris. That was great.
Yeah, if you have any other doctors that are as conversational as you, send them our way. Everyone, I really appreciate you watching this. Thank you very much for your time and have a great night. Bye-bye.